This lesson is on probability and odds. So let's start with our first sample. In a card game, you're dealing the first card from a well-shuffled deck. Find the probability of each event. In the first one, we want to know the probability of dealing an ace or a jack. So we want to find all of the favorable outcomes first. Here we have our deck of cards. So we've got all of these aces here. And then we have all of the jacks here. So there are 1, 2, 3, 4, 5, 6, 7, 8 favorable outcomes out of the 52 cards. So the probability of drawing an ace or a jack is 8 out of 52, which simplifies to 2 out of 13. Then we want to look at the probability of dealing a face card or a spade. So we want to look at all of our spades. There's our spades and all of our face cards, Jack, Queen, King. And we see we have a little bit of overlap there, so we want to be careful not to count those cards twice. So we have ace through 10 here in this first block. There's 10 cards, and then there's 12 cards here for a total of 22. So 22 out of 52, which simplifies to 11 out of 26. Let's look at that first one that we did, the probability of drawing an ace or a jack. Since you can't deal a card that is both an ace and a jack at the same time, these two events are what we call mutually exclusive. To find the probability of two mutually exclusive events, you find the probability of A and the probability of B, and then you add them together. So the probability of drawing an ace was 4 out of 52. The probability of drawing a jack was 4 out of 52. And when we added them together, we got our probability 8 out of 52. Now, when you're just looking at all the cards, you can certainly just count. We had 4 aces and 4 jacks, and so we just added those together. But we don't always have that right in front of us, and so this is a good technique to use as long as the events are mutually exclusive. They cannot happen at the same time. Are the events of dealing a face card and dealing a spade mutually exclusive? So let's go back to that first picture. We had all of these as our spades, and then we had this over here as our face cards. Could we deal a card that was both a face card and a spade at the same time? Sure, that was this set right here. So these two, drawing a face card and a spade, those are not mutually exclusive because these right here show how they can happen at the same time. Suppose you're choosing a card from a standard deck. How many outcomes are there for the event of drawing a heart? Well, how many hearts are there? There's ace through king, so that's 13 favorable outcomes. Out of how many total outcomes are there? Well, there's 52 different cards. So 13 out of 52, which simplifies to 1/4. What's the probability of drawing not a heart? Well, how many of the cards in the deck are not a heart? Well, if 13 are, the other 39 must not be. So for not a heart would be 39 out of 52, which simplifies to 3/4. Are the events a heart and not a heart mutually exclusive? Can you draw a card that is a heart and not a heart in the same card? Well, no. Either the card is a heart or it's not a heart. It can't be both. So yes, those two events are mutually exclusive. What's the probability for drawing a heart or not a heart? Well, for drawing a heart, the probability was 1/4. For not a heart, it was 3/4. If we add those, we get a probability of 1. Remember that a probability of 1 means that something is definitely going to happen. If you draw a card, it's either going to be a heart or not a heart. One of those things has to be what happens. Complementary events are mutually exclusive events that together contain all the possible outcomes. That example that we were just talking about, a heart and then not a heart, those two groups contain all of the possible outcomes of a deck of cards. So a heart and not a heart are complementary events. You might also say for a die has the numbers 1, 2, 3, 4, 5, and 6 on it. If I say an even or an odd, are those complementary events? Well, the first thing we have to know is, are they mutually exclusive? Can you roll a number that's both even and odd? No. So they're definitely mutually exclusive. Do these two groups together contain all the possible outcomes? Well, here's your evens, 2, 4, 6. Your odds are 1, 5. So together, even and odd contain all the possible outcomes. So for a die, even and odd are complementary events. Find the probability of not a face card when a card is randomly drawn from a deck. So you want to think of how many cards are not a face card. So we have ace through 10 of all 4 suits. So that's 40 out of 52, which when we simplify, we get 10 out of 13. Now there's another way to do this. We could find the probability of getting a face card and subtract it from 1. Since a face card and not a face card are complementary events, since together those two things contain all of the possible events. Here we've got everything that is not a face card, and here we have everything that is. You can see there's no overlap. That's mutually exclusive. You can see that together the two groups contain everything. That's complementary. So when they're complementary, you can use this method of 1 and subtract off the probability of the other. So the probability of getting a face card is 12 out of 52. So we could do 1 minus 12 out of 52, which is 40 out of 52. Again, 10 out of 13. For this example, it's not necessarily any easier to use method 1 or method 2. It might actually look easier here to do method 1. But I want you to keep this method in mind because sometimes it's a lot shorter to do method 2 than it is to do method 1. So we can also use the counting techniques and permutations that we just learned when we're trying to find probabilities. If we want to find the probability that no two people in a group of 5 have the same birthday, well, first we need to think about what that probability is going to look like. What is a favorable outcome for this? Well, we don't want anyone to have the same birthday, which means we want 5 different birthdays. Then what is the total outcomes? Well, that's all of the possible birthdays they could have. So, take this away. We see that favorable outcomes is the number of ways 5 people can have 5 different birthdays. And for our denominator, it's going to be the number of ways 5 people can have 5 birthdays. So let's start with 5 people have 5 different birthdays. Well, we've got 5, 1, 2, 3, 4, 5 people. How many choices do you have of days in the year for the first person to have their birthday? Well, we've got 365 days to choose from. But then we want person number 2 to have a different birthday. So now we only have 364 days to choose from. For person 3, we can't use either of those days, so we have 363 days, 362 days for the 4th person, and 361 days. And we learned in our permutations unit lesson that we can multiply those to figure out the number of ways 5 people can have 5 different birthdays. Now we need the number of ways 5 people can have 5 birthdays. Well, there are 365 days to choose from for each person. So there's 365 times 365, 365, 365. There should be 5 of those. Because anybody can have any one of those birthdays. If you multiply the numerator and denominator and divide, you get about 97%. How can you find the probability that at least 2 people do have the same birthday? Well, either they do or they don't. So this is kind of like complementary events. If there's a 97% chance that they don't, none of them have the same birthday, there must be a 3% chance that at least 2 of them do. The last thing we want to talk about is odds. We've talked about the probability of an event. That's the number of favorable out of the total number of outcomes. This is a part to whole relationship. But when we talk about odds, we're talking about the number of favorable outcomes to the number of unfavorable outcomes. This is a part to part relationship. You notice neither one of those has the word total. We have favorable over unfavorable. If you want the odds against an event, you do number of unfavorable over the number of favorable. Sometimes these are written as ratios instead, like unfavorable to favorable, or for odds in favor, it would be favorable to unfavorable. So suppose 2 out of 7 events are favorable. Well, that would tell us that the probability of getting that favorable event is 2 out of 7. But the odds in favor of that event are going to be, well, there's 2 in favor. There's how many against? 5. If 2 are favorable, then there must be 5 that are unfavorable. To find the odds against that event, the number of unfavorable, 5, to the number of favorable, 2. And I'm just switching back and forth between the ratio and the fraction so you can see both. In some ice skating competitions, the order in which the competitors perform is determined by a random drawing. Suppose a competition involves 5 skaters with different names. Find the probability the skaters will perform in alphabetical order. Well, if you take 5 names and put them in alphabetical order, how many ways are there to do that? Well, there's only one way to put a group of skaters in alphabetical order. So the number of favorable outcomes is 1. But how many ways are there to order 5 names? Well, if you're ordering 5 names, we learned last time that would be 5 factorial because we're ordering all 5 names. So that's 1 out of 120. The odds in favor means favorable to unfavorable of the skaters performing in alphabetical order. Well, like we said before, there's only one favorable outcome because there's only one way for them to be in alphabetical order. If there's 120 ways to list them and one of them is alphabetical, there must be 119 ways to not do it. So we could either write it like that or we could write it like this. That's the odds in favor of the skaters performing in alphabetical order. That's it for this lesson.